Okay. Sorry, can everyone see my presentation?
Yeah.
Okay, thank you. All right. So as I mentioned, today's lecture will be on electrochemistry. Okay. So this is more an introductory course into electricity. So the more currents and voltage and all of that stuff will be covered next week when we talk more about the physics side. This week is just going to be more so what you learned in general chemistry regarding this with the galvanic and voltaic cells. Okay. All right. Okay, let's get into the introduction. All people are coming in. If this is your first time joining, my name is Mark Abdurrahmanov. I'm a graduate of Stony Brook University with a Bachelor of Science in Biochemistry. My MCAT date was this January, and I scored a 520. My contact information is this email provided. If you have any questions with any practice tests or any practice questions or anything in general, please feel free to email me, okay? So a quick description about the course. So it's a 15-week full course, 3 lectures per week, Thursday, Friday, Saturday, and 1 office hours per week for now. Sundays at 8:30, but the day and the amount of office hours may change, okay? We'll be covering most of the highest, sorry, everybody, could you please mute? We'll be covering most of the highest yield MCAT content over the 15 weeks and the 45 lectures. And all lectures will begin at 8:30 p.m. Eastern Standard Time, just like they are today, okay? We also have a group me with the link. We'll be posting it in the chat towards the end of the lecture, or if you have the PowerPoints, you can do it that way. Group me will have all the lecture recording links and PowerPoints posted. After each session, we'll also be posting any updates or changes to scheduling here. It's an easy way to get a hold of me or Tim or any of the other tutors rather than email. You can just simply add us with your question. There's also other students there that will be happy to explain any questions you may have as well, okay? Okay, so learning objectives for today is we're going to be focusing on reduction and oxidation. We'll be talking about balancing redox equations. We'll be talking about what a galvanic cell is, and we'll also be covering very briefly what an electrolytic cell is and what the difference is between that and a galvanic cell. We'll also be talking about how we can calculate voltage across a galvanic cell, okay? So moving on to the content. First, we want to talk about redox reactions. So like I mentioned before, redox stands for reduction/oxidation reactions. So reduction and oxidation are processes in which a molecule either gains or loses an electron. And this seems like a very general description. And in fact, most reactions that you will see on the MCAT are redox reactions. I would say a good majority, other than even in organic chemistry, most of them are redox reactions. When you look here, reduction just means you gain electrons, and oxidation means you lose electrons, okay? And it's written here, so reduction and oxidation, the process either gain or lose in that order, okay? So if you want to look at this example here on the bottom, it's zinc plus copper 2 plus goes reacts to make zinc 2 plus and copper. If you notice in the start, zinc, and ignore the words on the bottom, we'll cover that in a bit, but zinc at the start has a charge of neutral, 0, right, because it's in an atomic state, and at the end of the reaction, it has a charge of 2 plus. Yes, and David mentioned oil rig. We'll be talking about that in a second, the mnemonics. And so as you can see, like it went from 0 to 2 plus. What are the only ways an atom can gain a positive charge? Well, it's not really the transfer of protons, because we don't really do that in chemistry. We only really talk about the transfer of electrons. So to get from neutral to plus 2, you would have to lose 2 electrons, lose 2 negative charges, right? And then you would have 2 more protons than you would have electrons, and that would give you an overall charge of plus 2. So what that means is zinc in this reaction has actually been, has lost electrons, so it has been oxidized, right? Copper, on the other hand, started off as copper 2+, meaning it was already had 2 less electrons than it had protons. And then at the end, it became neutral. So that means it couldn't have like lost protons. So that means it gained electrons, right? It was lacking 2 electrons, and then it gained those 2 electrons back, meaning it gained, right? So it got reduced. And here's the acronym or mnemonic that David mentioned in the chat, oil rig, and it stands for oxidation is loss, reduction is gain. For now, we're only going to be talking about electrons, but we will be covering H+, which is a proton as well in a bit. And this works for that as well, but oxidation is loss, reduction is gain in terms of electrons for now. So again, going back here, zinc lost electrons, so it's oxidation. Copper gained electrons, so it's reduction. Okay. Next, I want to talk about reducing and oxidizing agents. So as you can see, zinc itself got oxidized in this reaction, and copper itself got reduced in this reaction. But zinc, as you can see here, is a reducing agent, and copper is an oxidizing agent. It's the opposite. Why is that? Well, and we'll go back here. It's because electrons must go somewhere or come from somewhere. You can't just lose electrons and then they just disappear. You can't gain electrons like out of thin air, right? They have to come from somewhere. If you reduce something, if it gains electrons, that means something else had to be oxidized and had to lose its electrons for something else to gain. Same thing with oxidation. In order for something to become oxidized, to lose electrons, those electrons have to be gained by something else to make that thing reduced. Because of that, anything that itself gets reduced or gains electrons causes something else to lose electrons, right? Because the gained electrons have to come from somewhere. That's why it's a reducing agent, because it reduces other things. So zinc itself got oxidized, but it also caused copper to become reduced. Copper, on the other hand, itself became reduced, but it also caused zinc to become oxidized. That's why it's an oxidizing agent. Okay. And as a note, reduction and oxidation can also refer to gain or loss of H+, which is a proton. And in terms of biology and organic chemistry, that's what you're going to be talking more about. In terms of general chemistry, it'll usually be electrons, and electrochemistry, which we'll get into in a bit. It'll mostly be electrons. But in terms of organic and biochemistry, it will mostly be H+, which is a proton. But the same rule applies with oil rig. Oxidation is loss, reduction is gain. So if you lose an H+, then it's oxidation. If you gain an H+, it's reduction. The reason this is because if you add H+ to a molecule, like for example, you just had regular oxygen, right? You turn it into OH. You're reducing the actual oxygen itself. It went from a neutral charge to a minus charge, right? It actually got reduced itself. Okay. Same thing if you took an OH. If you went from OH to O, you're actually just oxidizing it. Okay, because you lost. Right, the oxygen itself is getting oxidized, and the hydrogen itself, the proton, is usually a reducing agent, right? Because it itself gets oxidized. Okay. And I'll get to questions in a little bit. I just want to get through like this little part. Balancing equations, this should also be a review for you guys. It's very simple, and the rules are exactly the same as they are for stoichiometry. No electrons can be created or destroyed, just like no molecules or atoms can be created or destroyed. So you must have an equal number of them on both sides. In order to do this, we have these things, we break things down into these things we call half reactions. So if we look at this on the bottom, this is a full reaction, Fe2+ plus C4+ goes to Fe3+ and C3+. that's a full reaction, but we break that down into half reactions, right? And we break it down into two parts. One part is the iron, one part is the CE. The iron went from 2+ to 3+. And again, if you notice 2+ to 3+, that means it's more positive. That means it must have lost an electron, right? It's oxidation. So if you initially had one iron, and then you split the iron into, you can split the iron into a more positive iron and an electron, right? You split it apart, and so the electron goes on the right side, on the product side. Whereas with Ce4, which got reduced, you took Ce4, then you took an electron, the electron fused with the Ce4+ to make Ce3+, so it goes on the left side. Then what you can do is you just simply combine these two half reactions, and I'll even annotate this for you guys. Anything on the left side and anything on the right side cancel out. One electron left, one electron right, they cancel out, and then you just combine these two and you get this full reaction, okay? And what happens if, for example, you don't have the same number of electrons? So for example, if we weren't doing 3+, we were going to Fe4+, right? We would need 2 electrons to be released, right? Well, now you have 2 electrons on the right, 1 electron on the left. You can't really have that. So how do you fix that? Well, you just multiply this whole thing by 2. So you'd have 2Ce4 plus 2 electrons and 2Ce3 plus, and you just simply multiply by 2. And in the final reaction, again, you just make 2, 2. That's if this was 4+ and you're using 2 electrons, right? This is just an example. Okay. Let's see. Okay. Next, a quick question, but first I want to get to any questions you guys may have. Okay. Does anybody have any quick questions that they wanted to ask?
When you went up with the oxidation state on the iron from 3+ to 4+, what was the net reaction? You kind of erased it a little quick.
Okay, no problem. So when it went to 4+, you actually needed 2 electrons, right? So from going from 2 to 4, you were releasing 2 electrons. Because that you have to multiply this whole half reaction by 2 in order to make the electrons balance out. You need 2 on the right side, you need 2 on the left. Yeah, whoever that is, please. Okay, then 2 electrons here, 2 electrons here, and then 2 here. And then the final reaction, this again, 2 and 2 are equal, cancels out, and then everything else just moves down. And then you just have 2 and 2, right? And this is just an example because this wouldn't really happen in nature, but sometimes you may see reactions with different elements where the electrons are not equal. And actually in the question, that will be the case.
Okay, great, thank you.
Any other questions from anybody before we move on? Okay. If not, I want you guys to try this quick question that I'm going to post. As a warning, this one is actually pretty hard. I think myself at least. So this may take you a while, and the one hint I would give is first break it into half reactions for sure, into an oxidation and reduction half reaction, and then note how even though this has like 2s and 3s in it, this reaction isn't balanced. If you count up all of the carbons, hydrogens, and oxygens, it's not balanced. So you have to balance it manually yourself. So I would suggest first thing you do is make a half reaction. Second thing I'd say is once you make the half reactions, balance it, and then try and figure it out. And keep in mind what I said about electrons or H pluses can also be used to measure reduction. Okay, I'm gonna start the poll. Okay, and if you guys have seen some of my old ones, you'll notice I add an extra option, which is E. If you really don't know or have no idea how to solve this problem, I'd like you guys to pick E rather than just guessing on one of the answer choices. Try and pick E's just so I have a better understanding of how things are going, okay? Or if you're running out of time and you don't have the answer and you don't want to guess, pick E, okay? But some people have already picked E, I see. But as a note, these polls are anonymous. But yeah, I'll give you guys a couple minutes, at least try out the question, try and get started. And we'll go over this in a couple minutes, okay?
Six plus one. This is 4.
Okay, please take another minute or so. Okay, another 20, 30 seconds, get your answers in. If you guys really don't know, there is an option for that, but try and see what you guys can get. Okay, and then the poll. So as I expected, most people chose actually, I have no idea. The vast majority of people had no idea. That's okay, because like I mentioned, this is I would say a very difficult question. It's probably harder than most questions on this topic that you'll see on your real MCAT. Correct answer is actually D, which no one really chose. But let's go over it together. Okay. So like I said, first thing we want to do is we want to break it down into half reactions. We notice that it's easiest to break it down this way. So break these two down into one part, and then this into another half reaction, and this into another half reaction. So like I mentioned, these aren't balanced. So I would just suggest just forgetting that completely for now and just doing it like this. And then now we can balance it. So 2 O's on this side, there has to be 2 O's on this side. You would have to do it this way. Then let's do the other half reaction is CH3. So the key was for this, I believe, once you reach this step, this first half reaction might have been easier, but this one would be a little more difficult. Where do you go from here? How do you balance it? So you see that there's a carbon, the carbons are balanced, one carbon here, one carbon here, but the oxygens are not balanced, so one here, two here. If you did this, now the carbons aren't balanced, even though the oxygens are, so you can't do that. So how do you get one oxygen on the left side without disrupting the carbon side? Well, what's a molecule that you know that only has one oxygen and no carbons? It's water, H2O. Now, if you look at it, carbons balanced, 1 to 1, oxygens 2, 2, balanced, okay? The only thing that's not balanced in both reactions is hydrogen. So there's 2 here, 3 here, 1 here. That's a total of 6. So you just have 6 hydrogens, H plus, on this side. And then on this one, there's 4 here, 0 here. So you just need 4 hydrogens. And remember what I told you, hydrogens can be a substitute in redox reactions for electrons, right? They could be, I guess you can think of it analogous. So now we can just find out how many electrons are transferred by balancing the two reactions together. Well, just like you would do in stoichiometry, you'd have to find the least common multiple or least common factor. I believe it's least common multiple. Least common multiple of 4 and 6 is 12, right? There's no other way to do it. So you just have to multiply this whole thing by 3. And I'll take questions in a bit. Let me just finish. And this whole thing by 2. And then what you're left with is the hydrogen. There's 12 of these, 3 times 4. So this cancels. There's 12 on this side because 2 times 6 cancels. H2O, there's 2 on this side and 6 on this side. So this completely gets canceled, whereas this gets taken down to only 4. And I'll do it in a different color, blue. This can be the final reaction. There's only 4 H2Os on the right side. CO2, there's 2. O2, there's 3. CHO3, there's 2. So what you're left with is 3O2 plus CH3OH okay. And but you really didn't even have to go that far. You know that the number of electrons exchanged, which is what they're asking about, was just the least common factor, which was 12. And so the answer was D. Okay. Okay, now I'll take any questions in the chat. Okay. Does anybody need me to start from the beginning?
Please do.
Before you go into the
Okay.
beginning, isn't 12 the highest common multiple, HCF, the highest common factor? Did you want the least common? Because then 3 would be the least
Yeah,
common.
no, I mistakenly said least greatest common factor. It's a least common multiple, LCM.
Okay.
Which
the
is
answer would still be
so like
3
2 and 3 would be 6. 2 and 3 would be 6. 4 and 6 would be 12. So 4 multiplies by, like, what's the factor
Oh,
that
okay,
can go
12.
into?
Got it.
Yeah.
Makes sense. Got it.
That's 12. 12, yeah. Yes, and okay, so do people want me to start from the beginning? Okay. All right, let's start it. Yeah, I can see yes. Okay. First step, and again, I'm color coding it, just make it easier. We start with this. We want to again break it down into half reactions. This and this go together, right? Right? These are the only two that can go together because look, this is the only carbon, this is the only carbon. So that means this has to go into this, right? If you want to think about it, what turns into what, even though it's not really that way, but what turns into what, this is best paired that way because the carbons, whereas this 3O2 and this 3H2O are best paired that way because of oxygen. Even though this one does have oxygen as well, it's just best to pair these two, right? Okay. Now we just create the half reactions, right? O2 into H2O. This is a half reaction, right? But we do need to balance the half reactions in order to get this final reaction, this full reaction, right? We can start balancing this one. This one's fairly easy. There's 2 oxygens on the left, only 1 on the right. How do we fix that? Easy, just make this times 2. 2 oxygens on the left, 2 oxygens on the right. 4 hydrogens on the right, so you just need 4 hydrogens on the left. The way you do that is just you add 4 hydrogens. There you go. This is perfectly balanced, and you're done with this half reaction. Next half reaction, this one's a little bit more complicated. Okay, notice 1 carbon on the left, 1 carbon on the right. Carbons are good. You can't add any more, you shouldn't really add any more carbons on the left or right, if you can help it. But if you notice, the oxygens on the left is only 1. The oxygens on the right is 2. But if you multiply this by 2 like this, well, now you have 2 carbons on the left, 1 carbon on the right. It's impossible to balance now because if you multiply this by 2, it ruins it, right? So you have to find a way to add oxygens without adding any carbons. The best way to do that is by adding an H2O on this side, right? Because we already had hydrogens here in the, we already had hydrogens here in the thing, so we were going to balance with hydrogens anyway. We just can't use carbon, right? But we do want to use oxygen. So now if you look at it, 1 carbon on the left, 1 carbon on the right total. Oxygens, 1 here, 1 here. That's 2 oxygens on the left total, 2 oxygens on the right total. That's balanced. The only thing left to balance are the hydrogens. 2 on the left here, 3 on the left here, that's a total of 5, plus an extra 1 here, that's a total of 6. Now you just add 6 hydrogens on the right, and there you go. Carbons, hydrogens, and oxygens on both sides are equal. This reaction is balanced, okay? So somebody asked, what happened to the 3? Which 3 do you guys mean? If you mean the 3, this one, or like these, this is a final reaction. And I mentioned, if you count up actually the carbons and hydrogens and oxygens for here, this is not actually balanced, right? This reaction is not balanced. So you shouldn't use these. And you can just actually ignore them because we're going to be balancing the equation ourselves, right? That's what they want us to do. The one near O2 and H2O. Yes, yeah, like I mentioned, this is the final reaction. We're not using this, right? We're not using this reaction. The principle of conservation of mass means, no, because we're not using the principle of conservation of mass. We're using, well, we are in a way, but if you have H2 on the left, if you notice, this hydrogen, we just added water. This hydrogens are being here. Mass is not disappearing, it's just here. These 2 hydrogens are part of this 6. They're not leaving anywhere. We're not getting rid of the mass. We're still keeping the mass, it's just in a different form again. This oxygen also is not leaving. It's one of these two oxygens. So the mass isn't leaving, it's just taking on a different form, right? So you can technically add whatever you wanted to on the left side, as long as it's in some way present in the right side, which it is here, right? This oxygen is part of this CO2. It's one of these oxygens, right? And these two hydrogens are part of these 6 hydrogens on the right side, right? That's the whole reason we're balancing it, right? We're not creating mass, we're just adding something else that's going to be used in the reaction. Does that make sense, Opal?
Yeah, do you mind putting up that slide so I know what you said? Something it's easy because we're using some principle. What, and that's why I thought by you adding all these waters and just adding stuff, is that allowed to just add things?
You can add whatever you want as long as you add it to both sides.
I can't just add. How do I know what to add? What if I wanted to add carbon dioxide? Why you chose water?
Oh, you can add carbon dioxide here, right? Look, if you added carbon dioxide here, but the carbon dioxide doesn't react with anything, so you just have now, boom, there you go. I fixed it for you. If you added carbon dioxide on left, you just put a 2 right here, and there you go. You can do that completely.
So why did you choose water and not carbon dioxide? That's what I'm trying to figure. How do I know what to add? I know you said.
It doesn't matter ultimately. Look, because if I added carbon dioxide, so now look what we have. We have H2O plus CH. It doesn't matter. Like even if we added carbon dioxide instead of water, that works fine. Whatever.
Okay.
Actually, it doesn't, by the way, work because we're still missing an O. But look what would happen. We added CO2 here and we added CO2 here. Cancel this out. Cancel this out. We're just left with what we started with. That's like adding 5 to both sides. If you had like a math equation and you just added 5 to this side and 5 to this side, nothing would change.
Balances. Yeah, go back to that slide with what the principle we're using. Because somebody asked to, what principle are we using to do these? You said it's easy.
So it's the same principle as we'd used for stoichiometry. Remember, in stoichiometry we were just balancing things based on what they were. Like we were just finding like if there's 1 carbon on the left, there has to be 1 carbon on the right. 2 hydrogens on the left, there has to be 2 hydrogens on the right. Right? Like you can't get rid of an atom. You can't get rid of a hydrogen. If you had a hydrogen on the left, you have to have it on the right, just in a different form.
So it's the conservation of mass. Okay.
Yes. If you want to go like to its root, it's conservation of mass. But
let me be quiet then. Should at the end of the lecture, no problem.
Yeah. But like I mentioned, I'm gonna get rid of this. Okay. Does that make sense? Far like okay. We can add whatever we want on the left as long as we add it on the right. That's why we added water, just because it's easy, right? We were gonna put in hydrogens on the right side anyway because we had these 4. So we were gonna add hydrogens anyway. We were just gonna add 4. Now we just added 6 because we put our water on the left. Now we also have an oxygen here. Now look, this has 1 oxygen. This has 1 oxygen. It's 2. Now we have 2 on the right as well. That's balanced, right? You can see both these reactions are perfectly balanced, right? It's the same thing as essentially doing math. If you're doing algebra, you really just have to kind of like keep adding things, dividing by things, multiplying by things, factoring things out, just kind of like playing with it until you get something that works, as long as you're not breaking any rules. And we haven't broken any rules because everything we've added on the left, we've added on the right. Once you get to this step, now you have 6 hydrogens, 6 H pluses here, 4 here. You have to make them the same number, right? That's at least bigger than 6 or 4. You have to make them like an equal number. The only way to do that is, well, there's many ways to do that, but the best way to do that is multiply this by 2 to get 12, because 12 and 4, both 6 and 4 can become 12. Multiplied by 3, multiplied by 2. So we multiply this one by 2 to make 12. We multiply this one by 3 to make 12. This is 12 hydrogens. Well, this cancels out with the 12 hydrogens here. Now we just have 3O2, and now this becomes 6 H2O. This is now 2 H2O, but we have an H2O on the left, and we have an H2O on the right. These can actually cancel, so we can get rid of this completely, and this goes down to actually 4 instead of 6, right? So now we have 4 H2O on the right. We have 2 H2 H3OH, right? Then we have 2 of these. Now, there's nothing more we can cancel out because there's no like terms, if you want to think of it that way in algebra. There's no like terms. So now simply we just add them together. 302 on the left, 2, call it math, but it's this one. So this thing is, I'm just gonna call it math. And then you have 2 CO2 on the right, plus 4 now H2O on the right. And if you want to look at the numbers, this one, how many hydrogens does it have? 3 plus 1 is 4, times 2 is 8. 8 hydrogens on the left because nothing else has hydrogens on the left. And now H2O, 4 times 2 is 8. 8 on the left, 8 on the right. Let's look at carbons. 2 here, 2 times 1 is 2. 2 here, 2 times 1 is 2. Hydrogens, carbons, balanced. Oxygens, 2 times 1 is 2, plus 3 times 2 is 6. That's 8 on the left. 2 times 2 is 4. 4 here. 4 times 1 is 4. 8. 8 on the left, 8 on the right, balanced. That works out. But the reason we care is, and the reason the answer is 12 is because how many of these did we get rid of? And we got rid of 12. Okay, but I'm showing you how to balance as well because that might be important. But the way you didn't even need to do this step like this. You didn't need to do this full reaction. You could have stopped here as long as you know that there's 12 of these, 12 here, right? The answer is 12.
Mark, I have a question.
Okay.
But isn't that protons though? It says electrons. So
yes, I mentioned that H plus, which is a proton, it can be analogous to an electron because of the way it's just the way it reacts with as like a reducing agent. It can also be a reducing agent, just like an electron is a reducing agent. Electrons are essentially just reducing agents, right? And H plus can also be as a reducing agent. It's going to be way too long, way too complicated if I explain to you like why it is. Just recognize that it is. H plus can also essentially be equivalent to an electron. And if you are moving H pluses, you're also moving electrons, right? Think of it that way if you want as well. If you're moving H pluses, you are also moving electrons, and in equal amounts. So 12, you're moving 12 H pluses, that means you're also moving 12 electrons. Exactly. Once you have determined the, somebody mentioned in the chat, once you've determined the LCM, you've determined the amount of electrons transferred. Exactly. Okay, I'm going to move on. If you guys still have questions on this, because I can't take forever on this. If you guys have questions, please stay after, or you guys can ask David, the other tutor, or go into a breakout room with him. Okay. We're going to be moving on to galvanic cells. Right. And as I mentioned, this is a really, really hard question. This is harder than almost any question I've seen on the MCAT that deals with redox reaction, anything like that. Most of them are much more simple. This one is very advanced and like requires a lot of thought. Okay, we want to talk about galvanic cells now. This is what a galvanic cell looks like. You guys have probably made one of these, or at least seen one of them in your general chemistry class here in high school or college. So a couple things you have to look out for. One, the salt bridge. It always like is the first thing I look at. This just is like a tube, I guess you can think of. It has like plugs, so not everything can get through, and it just allows the flow of ions between the two beakers. Then you have this liquid in both beakers, the solution, right? In this one, there's copper nitrate. This one, there's silver nitrate, right? It's just a solution that contains some kind of metal ion, right? Which is like, in this case, it's the copper 2+, and here it's the Ag1+. The anode and the cathode, which are extremely important. It's just a stick of copper and a stick of Ag in the water. And one of them, the anode is negatively charged, the cathode is positively charged, right? Okay, but we're gonna talk more about this in words just to make it clear. So we talked about redox reactions, and the way a galvanic cell works is it takes a chemical reaction, which is this redox reaction, this transfer of electrons, and it uses this chemical reaction to actually produce electrical output, right? It's produce electricity, and that's what's read on top of this voltmeter, right? Just like when you have maybe a chemical reaction, when we talk about thermodynamics, you have a chemical reaction that produces energy, it produces joules. Some chemical reactions, these redox reactions actually, with the flow of electrons, they can produce a current, a voltage, right? Just like a normal chemical reaction can produce energy, right, or heat. So we can actually use this type of cell to make electricity for ourselves, okay, using this redox reaction. An important acronym or mnemonic or whatever to know is REDCAT and ANOX. This is extremely important. Reduction always happens at the cathode, and oxidation always happens at the anode. So before we had this full reaction that we broke into half reactions. Well, now we're actually separating out this half reaction physically. So if you notice, the anode is here and the cathode is here. Well, we're separating, so oxidation happens here in this tube, and then reduction happens right here in this tube, right? We're splitting the two half reactions physically by location now, okay? And it always follows this rule. Reduction always happens at the cathode. Anode is always the site of oxidation. Use REDCAT, reduction, cathode, anox, anode, oxidation. Remember that the anode and the cathode are pure elements, so they're in their atomic form, they're in their neutral form, right? In the solution, the metals are charged, they're ions, right? So just like we had here, if you see in the solution, it's copper 2 plus and Ag plus, whereas in this stick, it's Ag, and in this stick, it's copper, right? Just regular copper. And you can actually see this happening. So the copper is 0. In the stick, you can see with this arrow is becoming copper 2 plus, right? It's going from neutral charge to a positive charge, meaning it's losing electrons, meaning it's oxidation at the anode, right? So you're actually taking copper from the stick and putting it into the solution, and you're charging it. And then you also have this on the other side, on the cathode, you're actually taking this charged Ag, and you're actually turning it into just uncharged Ag in its elemental form, and you're going from a positive to a neutral. Going from positive to neutral means you're gaining an electron, meaning it's reduction. Reduction at the cathode, oxidation at the anode. Can't stress that enough. That'll help you with a lot of questions regarding galvanic cells. Now let's talk about the electrical output. Each reduction oxidation reaction, half reaction, creates a certain amount of electrical output, just like most reactions have a thermodynamic output in joules, like I mentioned before. We can use known values of separate reduction reactions and combine them to find the total electrical output of a cell. And I'll give you an example here. So we know, and this isn't using metals, which is what we usually use, but it's a good example that I found. So we have this O2 neutral, so it's neutral going into 2H2O plus, right? And you're using these electrons, right? These 4 electrons. So this is, by convention, we always write the reduction reaction when we're giving this, right? We never write the oxidation reaction. We always write the reduction reaction, even if it itself is an oxidation reaction. It's kind of weird, but you'll see exactly what I mean. So this is a reduction because you're getting electrons, right? And it produces a current of this many volts. When this reaction occurs, it produces this many volts of energy, right? Or not energy, of electricity. Then you have this Cl2 again plus, so it's again reduction. There's Cl minus, you're producing this voltage, right? But we know that for a galvanic cell, we have to have both a reduction and an oxidation reaction. We can't just have 2 reduction reactions, right? So how would we make this galvanic cell if we were to? Well, we know that the purpose of a galvanic cell is to essentially create as much voltage as possible, right? If we want to create as much voltage as possible, we want to use the reduction reaction that will generate the most voltage, and we want to use the oxidation reaction that will create less voltage in its reduction form. And I'll give you an example. this Cl2 creates more voltage than this reduction reaction. This Cl2 creates more voltage than this reduction reaction of O2. So if we were to make a galvanic cell using just these two elements, we would use this Cl2 as the reduction, right? We would use this as the cathode. And this we would use as the anode, because even though it does produce a current, a voltage when we make a cell, it doesn't produce as much as when we use Cl2 as reduction. And we know one of them has to be oxidation, right? We have to make one of them the oxidation. Well, so we would just have to flip it, right? If we were going to use this as the oxidation, the O2, we would just have to flip it. So instead of going this way, we're now going this way. We instead start off with water and we go towards the left, or if you want to, you can just flip all the elements that way. To get an oxidation reaction, we start with the water and then we oxidize water to make O2, right? Instead of reducing O2 to make water, we oxidize O2 to make, we oxidize water to make O2. How would this change the electric potential? Well, it would just simply negate it. So electric potential is now negative 1.23, right? To go forwards is 1.23, to go backwards is negative 1.23, right? If we were to make a galvanic cell using these two, this anode and this cathode, right, using these two reactions, all we would have to do to find the total voltage produced by this cell is we would just have to add these two together, right? So we just have to add the 1.36 with the negative 1.23. You may see in some you may see you take the E standard of the reduction minus the E standard of the oxidation. You use subtraction without negating it. So what I did was I flipped it and I negated it to make it negative, and then I added. In some textbooks, you may see take this positive number, keep this as the way it is as a positive number, and then just subtract it. I don't like doing that. I think it's more confusing. I think it's easier to do it this way. Just flip it and then negate it. Makes it easier for me, but up to you. Just don't forget, if you do it my way, you have to add. If you do it like the way some textbooks or some books may say, you have to subtract. But yeah, keep that in mind. And when you add these two, negative 1.23 and 1.36, you just get a total of 0.13 volts. And that's the total voltage produced by this cell if we use this as the anode and the cathode. As you can see, this is not a very good anode. This is not a very good cathode. These aren't very good. 0.13 volts is a very small amount. That's why it's not used. If you had, for example, a number that was already negative. So for example, if we pretended that this reaction, there are some metals that are like this, where the reaction itself, the reduction reaction, is already a negative voltage. So again, we want to flip it to go towards the left instead of the right, and we would still be negating the sign. So we would actually be making it positive, and then we would still be adding it, right? Now we have 2.59 volts produced by this, right?
Is that the original? Is that the original going forward that you just did?
So the negative 1. So what I'm saying is pretend that it was different. So reduction of oxygen is like, this is not a really good galvanic cell. Like this produces almost no voltage. There's some metals, and that you'll see that the reduction itself, without changing any signs, without doing anything, are negative, right? And then you would have to flip it, and then you would have to negate the sign to make it positive. And then when you add them, it gets actually a bigger number. And those are the ones you want to use, right? That's how you want to maximize the voltage you get. Like in a battery, nobody's using oxygen or chlorine in batteries. People are using lithium because lithium already has a negative number, right? So if I want to clear this, if we were pretending instead of oxygen, this was like reduction of lithium, it's like negative 1.23 initially. Then when you flip it to make it go towards the left, it becomes positive. And then you would add it, because after negation, you always add. and then you get 2.59, right, volts, and that's a lot. And that's what a good galvanic cell looks like. A good galvanic cell looks like. Okay, but in this case, you would negate, when you would negate it, it becomes negative, and then you add it and it becomes smaller. Another thing I want to point out, and that's important is, and that they will often trick you up on, is notice how there's 2 electrons here and 4 electrons here. When you flip it, so you flipped it already, there's 2 on the left, and then there's 4 on the right. So you have to multiply this by 2. So this cancels out, and then this is actually 4, right? So you think, based on what you know from thermodynamics, that you multiply this by 2, right? Because it's you multiply the voltage by 2, but no, you actually don't do that. In galvanic cells, you don't care what the coefficients are. Like, even if you scale it, so like here they ask you write the balanced equation, so you would have to write the balanced equation, and you would have to recognize that, but it wouldn't change the E values, right? It wouldn't change the E values. The E value is still exactly the same. It doesn't matter if you multiply this by 2, by 10, by 100, the E value doesn't change. I'll go over this in a little bit better. I'll go over this in a little bit again, because it might have been confusing, but I'll go over this again.
Why did you choose that as the anode? Why did you choose the
okay,
the 1 point,
so
the anode versus, yeah? You said the one with the
right,
least?
because this one has a higher. We know that the cathode is the one that's going to be reduced. The anode is the one that's going to be oxidized. If you notice, both of these are for reduction, right? Both of these are being reduced, right? This one is better at being reduced. This chlorine is better at being reduced because it has a higher voltage. So we want this one to be reduced. Well, if we know that this one is being reduced, that means there's no other choice but having this as the one that's being oxidized. So that's why we chose it as the anode, because it's worse at being reduced than the other one. This one's better at being reduced. And then the one that's better at being reduced is the one that has a higher EV, right? Or E standard, right? I want to talk about quickly why it doesn't matter what the coefficient is, and an important equation that you guys may encounter. It's not as common on the MCAT, but in case I do want to teach you, it's called the Nernst equation. Nernst equation for E, and it's delta G equals negative NFE. F is a constant. I believe it's Faraday's constant. I'm not even going to give you the value for it or anything like that, because there's no way they're going to ask you to remember it. They'll always give it to you, right? So there's no point in even memorizing it. It's like some ridiculous number that there's no way you're going to remember. But it's a constant. It's always the same. N is moles, right? And this is if they give you, say, E and N, and they want you to find delta G, you would use this Nernst equation. For our purposes right now, we're going to be trying to figure out how this relates with E. So we want to rearrange this so E is isolated on its own. And E is this E, by the way. E equals negative, if we isolate it, rearrange it, E equals negative delta G over NF. We know that when we double the coefficient, delta G does double as well. It's exactly proportional. So if we were to go from CL, this has like a delta G of, say, 10 or whatever, or like negative 10. And then if we double this, now the delta G is higher. It's like negative 20. So you actually would, and this is like what we expect, right? And that's why you would expect E to change. But if you notice, you multiplied delta G by 2, but N is moles, right? And the moles have also doubled, just like delta G. So while delta G has doubled in the numerator, moles in the denominator has increased by the same amount, has doubled, right? That cancels out, and that's why E remains the same. So if you double the coefficient, delta G doubles, but N also doubles in the denominator, and then they cancel out. Ultimately, E doesn't change; it stays the same, right? And that's an important note. Does that make sense?
I have a question. So if they give you both of the equations like as oxidation instead of like reduction, and then both of the reduction potentials are negative, then would it be the more positive one that you would change, or like how would you go for that one?
I would honestly never see them doing that, because this is just like the way they write. The reason they write this is because, and the reason I gave it to you this way is because it's like the standard way. It's like the correct way of writing it. It's just like the accepted way. If they did give it to you in that way, if they gave you the oxidation reactions and they say we're both negative, all you would have to do is, if you wanted to make it easier for yourself, if you learn it this way, is just flip both of them. Flip both of them to make them reduction, just like they are now, and then negate it, so just make them positive. And then from reduction, you would find which one is more positive, and then you would just flip the other one back, right? That's how I would do it, because I always learned it through reduction. So I would switch both of them to reduction, compare both of them using reduction, and then switch one of them back to oxidation, right?
Okay.
Rather than, yeah.
Okay.
Confusing myself, yeah,
Thank you.
no problem. Okay, I want to move on a little bit. We were gonna go over this. Actually, there is a quick question. So actually, if you guys have any questions about this, please feel free to ask right now, because we do have a quick question. Okay, if no questions, I'll be moving on. Okay. And this question is much simpler than the last one. I know the last one might have scared you guys, but this one's a lot simpler. But it's much more straightforward. And I think you guys will be able to figure this one out. So I'm going to start the poll. I won't give you as much time as before, but yeah. Okay, poll should be open. And again, if you really don't have no idea, please pick E. Okay, I'll be ending in yeah, I'll be ending in a bit. So please get your answers in if you haven't already. Okay, last chance. Okay. Okay, so I'm happy. The majority of you picked C, which I'm happy about, right? And it is the correct answer. And I'm glad that the majority of you guys at least gave it a shot. Even if the answer wasn't completely right, it's okay. We're here to learn, and I'll go over this, and hopefully you guys will be able to understand it. Okay, so we know that this is the reaction that they give us. So you don't even really have to find which one is being reduced, like which one is being reduced or which one is being oxidized. They actually tell you. So this is good on this part. But we're given the reduction potentials for PB and Na plus. Like I mentioned, some of them are negative, right? Just like I said before. What you would do is this one stays the same because it's being reduced here in the half reaction. It's being reduced in the actual reaction. Just keep it the same. Don't touch it. This one is being reduced in the half reaction, but it's being oxidized in the real reaction. So what all you simply have to do is negate it. And you just make it positive. Now, once you do that, all you have to do is just add these two numbers together. When you add negative 0.13 and positive 2.71, you get C. Some trap answers, D. The way you would get D is you would look at this coefficient, 2 times Na, right? The reason you would think that is, well, if there's 2 Na, so obviously you multiply this by 2, so that means this would be multiplied by 2 as well, right? That's what you may think. But like I mentioned, with electric potential, never do that. That's always the wrong answer. And that's every time they give you a question like this, they'll always have that as an option because they want to trip you up, because that's how it is for thermodynamics and for delta H, delta G, delta S. That's how it is. For this is not how it is. For voltage, that's not how it is. For voltage, doesn't matter what the coefficient is, it always stays the same. Okay, and I explained why that was, and it's due to the Nernst equation, right? Okay, why is A not the answer? So B, I'm glad nobody picked, and honestly, you could have kind of found A, narrowed down to A or C before, but why is it not A? Well, this is because this is being reduced in the half reaction. Look, this is a PB2 plus 2E is PB. This is being reduced in the half reaction, and then in the real reaction, it's also like that. So you don't have to touch it because it's already in the form you want it to be in. This one is in a different form, right? Because here it's NaS, and on this side it's Na plus, whereas here it's on the left side is Na plus, the right side is NaS. So in order to correct it, you would have to actually switch the arrows around. If you switch the arrows around, you have to negate. Right, I'm going to erase that. You have to negate. Negative turns to positive, and you get positive 2.71, right? Does that make sense to everybody? Okay. Now, let's pretend that they didn't give you this, right? If they asked you to figure that out on your own, right? That they didn't give you that. How would you determine which one is being reduced and which one is being oxidized? Well, you know that the one, what this number means, essentially, you want to think firstly, what does this number actually mean? What this number means is when I do this reduction reaction, how much electricity am I making from doing this reaction? As you can see, from this one, you're actually not making any, you're actually losing a little bit. For this one, you're losing a lot of electricity, right? If you were to perform this reduction reaction, you were gonna lose a lot of electricity. You'd have to actually pump in electricity, right? What you want is you want to have the reduction be the highest number, right? In terms of like a number line, the highest number, the one that's most to the right. This number is higher than 0.13 is higher than negative 0.13 is higher than negative 2.7. So you want to use this as the reduction, right? Because it's higher, right? It's closer to positive. Okay. if you use this as for reduction, the other one has to be used for oxidation. There's no other way. You have to have one oxidation, one reduction. Can't have both reduction, can't have both oxidation. So then what you would have to do is you would have to use this one for oxidation, and that means this one is going to be the one that gets flipped. Right? And that's it. And then you could just get this full reaction from that. Because you would keep the PB from here, from this left side, the PB2 plus. Because you flip the arrows, now the NaS, the Na like neutral is on the left side because the arrows are flipped. Again, you have to multiply by 2 because there's 2 electrons here, only 1 here. So you have to multiply this whole equation by 2. And then you just get PBS, this one on this side, plus, since it's flipped, Na plus. Okay, does that make sense? That's how you would find it if you were asked. Any questions about this problem? Is it more clear to everybody?
So Mark, if you told us, sorry. Turn this to
Wait, could you mute the other one?
Yeah, you said we could just, if we didn't know which one was the oxidation and which one was, we could just flip both of them, you said, and turn them into.
No, don't do that. Don't do that. What the question was asked was, if you see how this one, they gave you both of them reduction. So like here, this one's reduction and this one's reduction, right? And that's the convention. That's how it's normally written. That's like the standard way it's written. What the question was that was asked was, what if instead they gave both of these reactions as oxidation reactions? What if like the question had both of them flipped for you initially, and they gave you the V for the oxidation instead of the reduction? I said this would almost never happen just because it's like, it's not right. It's not like the right way to do it. But in case it was, all you would have to do is just flip it back to this, but you almost never have to worry about that, like I said, because it will always be given to you in this form. So don't really even like think too much about that.
Okay, thanks.
Yeah, don't worry about that. Okay. Okay, we're almost done. I just wanted to quickly mention electrolytic cells before we wrap up for today, and then I'll take questions at the end, any problems you guys have. Electrolytic cells are the opposite of galvanic cells. While a galvanic cell, I mentioned, it uses a redox reaction to create an electrical output, to create a voltage, and that's what we've been looking for. We've been looking for the reaction that has the highest, that creates the highest voltage. An electrolytic cell is exactly the opposite. An electrolytic cell is, you actually are using a battery. You're using electricity to make a reaction happen. Instead of using a reaction to make electricity, you're using electricity that you already have to make a reaction that wouldn't normally happen, right? One important difference is the sign of delta G of the reaction. So for example, all the reactions we've been talking about for galvanic cells, they have a delta G of a negative delta G, meaning they happen spontaneously or they'll happen on their own. And because they happen spontaneously and on their own, they produce electricity, right? Whereas in an electrolytic cell, the reactions have a positive delta G, meaning that they won't naturally happen. They won't happen on their own. That's why you need to actually take a battery or any other electric source of electricity. You actually need to pump electricity into the reaction in order for it to happen. You need to add something in yourself for the reaction to happen. Another difference is the sign of the anode cathode. Like I mentioned before here, in a galvanic cell, the cathode is positive over here, positively charged. The anode is negatively charged. In a electrolytic cell, it's the opposite. If you can see here, the anode is positively charged, the cathode is negatively charged. Really, I wouldn't suggest like putting too much emphasis on memorizing like the cathode anode signs. It's kind of important, but it's rarely tested. I think like the actual signs itself, if you don't have it memorized, it's not too big a deal. If you have like the spacing, I guess, in your mind that you are not using for something more important, memorize it. It can't hurt. but it's not like too important, but just know it's different. Electrolytic cells, as you can see here, they don't use a salt bridge like they do here. They happen in one beaker, whereas in galvanic cells, there are 2 beakers connected by a salt bridge. Instead, electrolytic cells use a battery as a source of electricity. So if you can see here, and when we cover circuits, we'll talk, this is the sign for a battery, right? So you need to hook up a battery, otherwise this won't work. And the battery sends electricity into the cathode and like this in a circle. Whereas in a galvanic cell, since you didn't need to put in electricity, you're actually making electricity. The only thing they might have, and this isn't a requirement for galvanic cells, but most have it, is a voltmeter, which just measures the amount of voltage going through. Over here, it just measures how much electricity is being produced. Whereas in a electrolytic cell, you have to make the electricity to put in. In an electrolytic cell, positive charge on the anode and negative on the cathode, which I mentioned, while in a galvanic is reversed. Red cat and anox still apply, by the way. Even though the signs of the cathode and the anode are flipped, reduction always happens at the cathode no matter what. Oxidation always happens at the anode no matter what, right? It doesn't matter, it's just the signs of the actual sticks are flipped. Oh yeah, and you asked that in the chat, yes. Reduction always at the cathode, oxidation always at the anode. Red cat, anox is always applicable. Same thing as oil rig. Oil rig, whether they're talking about electrons or H+, oil rig applies. Oxidation is loss, reduction is gain. That's about it. I want to talk about maybe quickly about the purpose. And this is the last slide, by the way. So if you guys want, you guys are free to go after this. But the purpose of electrolytic cell versus galvanic cell. Galvanic cell is usually if you wanna make a battery. A battery is just a galvanic cell, right? Essentially, you take, or modern batteries not so much, but classic batteries, like old batteries, are essentially just galvanic cells. You have copper, and you have an anode and a cathode. Usually it's copper, and I think they use palladium or something like that. I don't remember what it was for the cathode or whatever. And you just create this, and it creates a big current, and that's how you from using a chemical reaction, you make electricity, right? That you can store, and that's how you make. That's what a battery is. It's just a storage of electricity. And whereas in an electrolytic cell, you already have a battery. You already have a source of electricity, but you want to make a reaction that doesn't normally happen. That's more for chemistry or biology. You would use an electrolytic cell, whereas if you're going for practicality in real life, like a battery or something, you would use a galvanic cell. For electrolytic cell, if there's say a really like tough reaction that never happens in nature, it's very hard to get to happen. Sometimes it's a redox reaction. It has to be a redox reaction, right? You can sometimes force it to happen just by putting in some extra voltage into the system, right? And it will get the reaction going. When the reaction wouldn't normally happen. Okay, those are just really like the main purposes. That's about it for today. Oh, Nernst equation, yeah, Nernst equation applies to both. And actually, if that's really interesting that you said that, because the Nernst equation, we can actually, it mathematically relates to this. We know that n is a positive number. Moles is always like, you can't have a negative number of moles. This is always a positive number. Faraday's constant is also a positive number, right? But you notice there's negative sign. If delta G of the reaction is negative, meaning that the reaction happens spontaneously, the E produced will have to be positive, right? Because if this is a negative number and there's a negative sign here, that means E has to be a positive number, right? And that makes sense. If it's a spontaneous reaction, it's a galvanic cell because the reaction happens on its own and it produces a voltage. It makes a current, right? The reaction itself makes a current. If instead, again, N is positive, F is positive. If the delta G was positive, meaning that the reaction is non-spontaneous, that means it doesn't naturally occur. You have a negative number here, That means E has to also be a negative number in order to make it a positive result. What that means is if the reaction doesn't happen in nature, the electrostatic potential is actually negative, meaning that you have to actually put in voltage, you have to put in electricity in order for it to happen, right? And that makes sense. And that is what an electrolytic cell is. You have to overcome the E. How long does it take for the recordings to become available to us? So it depends. This one is being streamed live on YouTube, so the unedited version should be available for you to watch whenever you want. If you are waiting for the edited version, it may take a couple of days, possibly 2 to 3 days for each recording. But it shouldn't really take longer than that, and it's on YouTube again.
How do we determine like a stronger oxidizing agent or stronger reducing agent?
Right. Well, okay. Are you talking about galvanic cells or in what?
Oh, I was working some problems with these cells.
Yes.
They gave us the chart you mentioned, the standardized.
Exactly. Yes.
And they asked which one was stronger. I mean, if they're, oh, I get it. Maybe the E0. Is that what tells? Which
exactly.
One?
Yes.
Oh, okay.
It's the E0. But think how, like, which one is it, right? So I can actually, can you pull that up, Opal, and just
sure.
Here,
You want me to share my screen? Is that what you mean?
No, I just have I have a blank page here. I'll just write it for you. I'll ask you, can you give me maybe 3 elements, one from the top, one from the middle, and one from the bottom of the list? Give me the reaction, or like the element that's being reacted, and the E0, right?
Oh, you want me to give it to you?
So yeah,
or I could just have you. I'll
one,
just it's on my screen. I could just have you let me share the screen, and I'll
actually, yeah, sure. Okay, so we are done with the lecture, guys, but we will be doing related questions right now if you guys want to stick around. Yeah, let me give you.
I think it's this one. Are you seeing it?
Can you? Okay. Yes, we see it. Yep.
Okay, that's the tough,
yeah.
The balancing. I'll have to sit with that one, but I think the one you wanted was question 5. Let me just go up, scroll up. This was it. That's the one they're asking. What's the, which is a stronger oxidant?
Oh, strongest acid. Yes.
So let me get rid of this, and so you can go from there.
So what does strongest oxidizing agent mean?
A good you said the oxidizing agent gets reduced.
Exactly.
So which is the agent?
The strongest oxidizing agent is which one is best at getting reduced itself. If you want to scroll up, right? And if you notice these half react. No, just this table, yeah. How do I annotate? Oh, okay. So if you notice that these half reactions, these are reduction, right? For itself, right? The reduction for itself. And this is how much voltage, when this thing gets reduced, this is how much voltage it produces, right? The higher the voltage, the better it is at becoming reduced itself. The better it is at becoming reduced itself, the better an oxidizing agent it is. So AU is the best one because it has the highest voltage when it itself becomes reduced, so it's the best at oxidizing.
Let me see if that was
these questions. These are where did you get these?
The answer is A for number 6.
Yeah, it's AU, yeah.
Because it has the highest voltage.
Exactly.
Okay. And,
wait. Can you go back down?
How far?
It would not be AU because it would be AU3 plus. I believe it would be AU3 plus. Because AU is already reduced, so it wouldn't be an oxidizing agent because it wouldn't get further reduced. It would be the thing on the left. It wouldn't be the thing on the right. If that makes sense.
Yeah, I think I read somewhere that
so it's not
AU, not in the product. So I need to do
exactly.
So could you
So
clarify?
if you want to scroll back
There
down,
was some reading I did where when you're looking for reducing agents, actually I have it right here. It's never going to be in the reactant. It's going to be in the, it's never going to be, I think I have.
yeah, I don't know about, so because if they ask you what is the strongest reducing agent, it would be in the products, it wouldn't be in the reactants.
It would not or would.
So it depends. So let's look at it this way. Which is the strongest oxidizing agent? What is the best at becoming reduced? Au3 plus becomes reduced. Au doesn't become reduced. It's already the reduced form, right?
Mm-hmm.
Au3 plus gets reduced. Au3 plus is not the option, so it's not A. A is wrong. PD2 plus, if you want, can you zoom out? Just like not scroll down, but zoom out so we can see both the table and
Okay,
the
zoom out.
options.
Which
It'll be the minus one.
oh, this is the zoom out? I think this is it, yeah. Oh, is that better?
Yes, exactly. Okay, so it wouldn't be Au because we are discussing, if it was Au3 plus, that would be the answer, but it's not. K plus, where is K plus? K plus is the worst oxidizing agent, so no. PD2 plus, that's pretty good. It's the third best on this list, and look, it's PD2 plus, so it's the one on the left. Very good. Fe, so Fe is right here, but notice it's not this, it's this. But if you were, yeah, so it's not that, it's this, so it's not this one either, because we don't know what it is, Fe getting reduced, right? So it wouldn't be C either, it would be B. The answer would be B.
Answer is B. Let me check really quickly. Yeah. He said 6 was B. Let's see.
Yes.
Question number 6 right here. It is B. Yeah.
Okay.
So that's how we determine it. All right.
Yeah. It's whichever one has the highest number, but also look that it's the correct one that they're giving, because that's a trick.
And we
right?
do the same for the reducing agent. The same.
So what does reducing agent mean?
It's the one that's most oxidized.
The one that, yeah, exactly, the one that gets oxidized. How do you determine which one gets oxidized the best?
If there's a increase in oxidation number.
Okay, yes, I guess that's right, yes.
Or is there another way? A small.
Yeah, yes. I was more referring to in like, yes, but I was more referring to.
If you know a better way, that just tell me.
No, it's not a better way. I was more referring to like in this sense, right? Well, you said it was technically correct, but it's I meant like what would it look like in an equation, right?
Okay, it will be on the
reducing. Somebody asked in the chat. Reducing number is oxidation. Oxidation is reducing number of electrons. Reducing number of electrons, so it's becoming more positive.
Positive. Okay, so the least negative number.
So yeah, which of these is the strongest oxidizing or strongest reducing agent? Strongest reducing. I'll give you the range first. Which one do you think? Guide me through your thought process, and I'll get to questions in the chat in a second. I just want to finish with this. I want to get through this question, right? And this question is for everybody. It's not just for her, even though she's the one asking it.
Yeah. So
what do you guys think? What do you think is like the thought process?
You said would be the one that has the highest E0, the most positive E0. So if I scroll up.
No, that's the strongest thing that's getting reduced itself, or the strongest oxidizing agent, which is what we just covered in 6. This is asking for the opposite, which is the strongest reducing agent, which is the best at getting oxidized itself.
Oh, so it's the least E0.
Exactly.
Which would be negative, negative 292.
Exactly. Well, yes, it'll be this one. But what do you think? Would it be? And everybody in the chat, feel free to also give in your opinions. Would it be K plus or would it be K0? That's best at being oxidized.
Again, in electron is oxidation, so it will be K plus.
I don't think so. I think it would be K0, right? K plus gets reduced, right? It gets an electron, right? K plus is receiving an electron here, right? They showed you, oh, this is supposed to be an E. K plus is receiving an electron, meaning it's getting reduced. K is being oxidized into K plus. So you even have like the right thing is becoming more positive. K plus doesn't become more positive. Otherwise that would be K plus, K2 plus.
Mhm.
K becomes more positive into K plus, sorry. So K is the best, is the strongest reducing agent because it itself gets oxidized.
That's not.
It might not be an option. So
That's
you would
not-
have to look at just whatever is the next best. Well, I can't see what is the D. Can you scroll down just a tiny bit more? Can't see what D is. Oh, Mg. Okay, so next, so you notice K is the best. What's the next best? Na. Well, that's not an option. Mg is the third best, so Mg would be the right answer.
Got it. Simple as that.
Yeah, and if you want to think of it a different, and I don't want to confuse you, so if you get confused, just forget what I said, forget I said anything, but if you actually flip it, so this is K plus going into K, but what if you flip it? K going into K plus an electron.
Gain of
What's going to be the E0?
reduction.
No, what is the number?
Oh, we flip it. So we're going to change it to plus 92. Plus 2.
Plus 2.92.
Plus
Yes.
2.92.
And now look, for oxidation, this is the best one at being oxidized because it has the most positive number, right? And now, does that make sense? So like the reason this one is the best at being reduced is because the reduction reaction, the reduction half reaction has the highest positive number. The reason this is the best at becoming oxidized is because it's the worst at becoming reduced. Does that make sense? If it's the worst at becoming reduced, that means it's the best at becoming oxidized. Exactly. But if you flipped it, and this is what this is what somebody asked before, if you flipped it to what I wrote here, it's now the best at being oxidized because it has the highest positive number. And this, if you flipped it again, would be negative 1.5. So it would be the worst at becoming oxidized and the best at becoming reduced. Does that make sense? And if anybody, if you got confused by that, just ignore I said anything and just keep it as is. But
quick question, Mark. We can, if somebody has have a question, that's fine. I could do this in office hour. You see this balancing? He gave us 3 different steps. Different.
Yeah. Okay. Yeah. Before we move on, I want to ask people in the chat questions. I want to ask people if they had questions on the actual content first before we get into like practice questions, and then if not, we'll go into practice questions. We have some time left, but I want to ask people if they have any.
Sure. Do you want me to stop sharing?
It's fine. Just you can keep the share. Just if anybody else, if anything, I'll ask you to stop so I can go back to the PowerPoint if anybody needs. Please, if anybody has any questions, please put them in the chat. Ask your own questions. Any clarifications? Anything at all? Question bank that I recommend. If you bought one, UWorld is good. Kaplan is okay. Anything like that is fine. Really, whatever it is that you bought, whichever one is best for you to buy. I think we have a discount on UWorld if you go on the GroupMe and ask. We should be able to do that. That's a pretty good one. Kaplan is fine. Berkeley is fine. I think the AMC one also has one that's obviously going to be the best one. The AMC one, because that's actually the creators of the MCAT, so that's like the most accurate. Yeah, those anything that you find is good, but I don't have anyone to recommend. Galvanizing cells, Anna, if you can you stop sharing screen?
Sure. Stop sharing?
Yeah, please. So I can go back to my PowerPoint. So galvanic cells, is there like specific thing you had to ask about that, or do you just want me to go over the whole thing as a whole, like this whole part? I'm gonna stop.